Hey everyone! So today, we're going to dive into the logic behind something we do every single day without even thinking twice about it: changing our minds. Now, it sounds simple, right? But it actually opens up a huge, fascinating question.
So let me just ask you this. When is it actually logical to change your mind? I mean, we usually think of logic as this super rigid, unchangeable thing. But what if I told you there's an entire field of logic that's all about being flexible?
Let's take a classic example to see what I mean. Okay, so you see a bird. Your brain instantly goes, okay, birds fly. That's a solid, reasonable assumption to make. But then you get a new piece of info. Oh, wait, it's a penguin. Instantly, you just drop that first conclusion. Now, you didn't make a logical error, you just adapted. And that simple, everyday act is actually a massive puzzle for traditional logic.
And that brings us right into our first section. We're going to look at the logic of changing our minds and really dig into why perfect logic, as we know it, can sometimes fall a little bit short.
You see, traditional logic, what logicians call monotonic logic, it works kind of like building a tower. Every new fact you learn is another block you add on top, and the tower of your conclusions just gets taller and taller. You can never, ever take a block out. But that's not how we think, is it? Our brains are constantly revising, updating, and rebuilding.
So, how do logicians actually create a model for this? Well, it's time to meet the hero of our story today, non-monotonic reasoning. This is a kind of logic that's designed to work a lot more like we do.
At its very core, non-monotonic logic, or NML for short, is built on this one simple but incredibly powerful idea. It is perfectly logical to take back a conclusion when you learn something new. It basically gives us the rules for making an educated guess and then changing it when we know better.
Now, what's really interesting about this slide is how clearly it just lays out the difference. With the old-school monotonic logic, your collection of truths only ever grows. But with non-monotonic logic, adding new information can actually shrink your set of conclusions because you're tossing out old assumptions that no longer fit. The logic itself is adaptive. And the source material puts it perfectly. This is the logic of common sense. It's what gives us the formal structured ability to do what our brains do naturally: jump to conclusions from available data. It's how we navigate a world where we never have all the facts.
Okay, so if this is what we want, how do you actually build a system of logic that can do this? Well, it turns out there are two main blueprints that logicians follow, kind of two different philosophies for how to construct these flexible rules.
The first one is called the fixed point approach. The easiest way to think about this is making a default assumption, like birds fly, and then you just stick with it unless new evidence comes along that flat out contradicts it. The second path is the semantic preference approach, which is a bit different. It's more like you consider all the possible ways the world could be, and then you just pick the simplest or most normal one. Now, the details can get pretty complex, but the big takeaway here is that logicians have found multiple, really solid ways to build this kind of flexible logic.
But just creating a brand new system of logic isn't quite enough. You have to be absolutely sure that it's reliable and that it behaves the way you expect it to. So, how do we know it actually works? How do you stress test an idea like logic itself?
Well, the answer is a field called proof theory. Honestly, you can just think of it as the quality control department for logic. It's the whole process of building these super rigorous, formal rulebooks to make absolutely certain that these new, flexible logics are sound and won't lead you down a path to contradiction.
And to get this job done, logicians have a whole toolbox full of cool methods. They use things like sequent calculi to create those rock-solid rule books. They analyze something called consequence relations to check the deep mathematical wiring under the hood. And maybe most intuitively, they build dynamic systems that can actually simulate a debate, which is really cool, and we'll see that next. And this brilliantly illustrates how those argumentative systems work. I mean, they literally mimic a conversation. A claim is made, like this bird can fly. Then a counterclaim shows up like, but this bird is a penguin. And finally, the system formally and logically withdraws or revises that original claim. It's a debate, but it's all written down in the language of logic.
So after all this theory, we have to ask the big question: why does any of this matter? Why would we spend so much time and energy trying to formalize something as basic as changing your mind? Well, as it turns out, this is very likely the logic of the future.
Because being able to formalize common sense reasoning is a monumental leap forward, especially for fields like artificial intelligence. Think about it. If we want to build machines that can truly navigate our complex, messy, and unpredictable world, they can't be stuck with rigid old-school logic. They need the ability to make assumptions, to learn new things, and yes, to change their mind.
And that just leaves us with a final and pretty provocative thought. the ability to update our beliefs when we get new evidence. It feels like a fundamentally human thing to do. So, if a machine can finally master this kind of logic, if it can genuinely change its mind, does that mean it can truly think? That's definitely something to chew on. Thanks for joining me.